Alright, hello everyone, I'm back. So, yeah, it's not possible to train today, so I decided to not train. I had my dinner and I read this one more time, the Hill-Holz's algorithm, and I kind of have an idea. Okay? I kind of have an idea. I haven't checked the solution or anything, so I'm gonna just keep doing this. I mean, I'm a little bit obsessed at the moment because it just didn't work, and I really want it to work. So here's what's gonna happen. Reading this again, right? The here Horse's algorithm says you will choose any starting vertex V and follow a trail of edges from that vertex until returning to V. And this is the most important part. It is not possible to get stuck at any vertex other than V because they're all even. Like for us, we don't start with any one. We start with the one that has odd number of odd degrees. So you start from the odd degrees and you start to go around. There are only two outcomes. One is you reach the other odd one. And if you go from a one odd and you reach the other odd, I guess that's okay. That actually should be the end. If you start from one odd and then you reach the other odd, I think that's the end, right? That should be the end. Yeah, I think that should be the end. Actually, now that I'm thinking about it, I'm not 100% sure that if that is the end. Right? If you start from this, because I can see how the thing can be um, handled differently. Hold on. Now that I'm starting to try to redo this, what if this is the start and this is the end? But then I can go through many other things. Well, I mean, of course, it's not possible because you need to go through the whole thing to get here, right? And then this is it has to one of them has to have an even number, odd number of degrees, and here everybody is even number of degrees, so I can do another one. So yeah, hold on. My question is it possible that we got stuck at the end, or when we get stuck at the end, is it possible that from there we can get out again and then coming back? So basically we'll here and do this. Yeah, it doesn't matter. Okay, it doesn't matter because you start from an odd, you'll end at an odd, or you end at yourself, right? So if you end at yourself, we just do it again. Do it again. Just keep doing it. And each time you do, you remove a child. Each time you do, you remove a child. You don't, basically, there's no backtracking. You just keep going, keep going, keep going. And at the end, you will exhaust all the edges for you. That's fine. Basically, you see, we start from here, we go back, right? We go and we go back and we go back and boom, done. I don't have any. And then you start from the other one, you do the same thing, but eventually it will have to connect, right? Because this will connect to the previous one. It's bound to, because this is how it's designed. So this is kind of the current idea, right? Of how we're gonna do this. So here I'm gonna changing it. So instead of set, actually I'm gonna call this a stack. I'm gonna use a stack, okay? And we're also gonna change this because I don't need a pair.length at this time. And just I'm gonna change this to a stack instead of a set. Okay, gonna be a stack, and this is not a hash set. It's gonna be a stack. All right. And here, this one I'm gonna change. We don't need to do this. Don't need to do this. Right? Don't need to do. What I'm gonna do is a while graph dot get all default node collections dot empty stack. They don't have empty stack. We can just say empty list. Right? Ooh, type mismatch. Damn it. That's fine. I can just do. Okay, I cannot do empty list. What should I do? Empty iterator. No. Damn. I cannot use any of them because there's no stack. Alright, I'll just say new stack. Right? So we say get all default, get this dot size. Right? Equal larger than 0. Oh, it's not empty. Is empty. Right? If it's not empty, okay. What we're gonna do is int child shall equal to graph.get node.pop. We pop the child, and then we do this. We add it to path, and we say tfs graph c path. Doesn't matter if it go return to the to a previous visit node, it's fine. We just keep adding it until a point where we cannot add no more, right? This shall be a void. So just keep going. Every time we'll pop it, we do it, we pop it, we do it, and eventually we're done. I think this one is not necessary. Right? I'll just graph, node, and then path. So otherwise, this one is gonna be we're gonna change this one completely. Just delete the whole code. Else, oh no, we delete this whole code. Right? Then we just we do one of them. Right? We do one of them. We say dfs graph node1 path. Okay, this will go through everything, and then we are going to check. And how to check? We say if path dot size is equal to is smaller than pairs dot size pairs dot length. That means we have more to go. Then we go graph node 2, a new path. Actually, we do need a new path, right? Yeah, we need a new path. So we're gonna say a list int path 2. Okay, then we'll dfs graph node 2 path 2, and once it's done, we're gonna merge the two. Now why you do that way, right? Can I say actually I don't know how to add all. Okay, so this is using using this algorithm. Okay, let's give this a shot. I don't understand. I don't understand. Not equal to. Are you kidding me? I don't think it's even getting in there. What the hell? I thought we're doing this. Oh, hold a second. Maybe there are two ways to do this. Maybe. Hold on. Not 100% sure still at the moment, but I do know we need to change this. Yeah, then we need to traverse, right? And then we need to traverse the tree and the graph. Traverse the graph. The traverse must hit each edge exactly once. We know the starting point, right? We know that the starting point must be one of the odd degrees or any of the even degrees if all nodes have even degrees. We use, I forgot the name, Hirholzer. We use Hirholzer's algorithm to do the traversal. Okay. So although it's kind of, it tell me it's wrong, but I think that's just because this test case might have multiple ways of doing it. We just submit it. We see if it works. It does not work. Okay. It does not work in the most basic case. Let's see. All right. 1, 2, 1, 3, 2 to 1. Output 1 to 3, 1 to 2, 2 to 1. Oh. Oh, I see. So, it makes sense. So you do it one way, right? You grab something, so it will end at the 1, and it could be this overhead this, or it could be the other way around. Okay, so yeah, this we can fix. So basically we do this, we get a path 2, right? Now depends on how path 2 and path 1 is connected, right? And then what we believe is path 2 will connect with path 1, but that's not necessarily the case. So we say if path 2 dot get path 2 dot size minus 1 is equal to path 1 dot get 0. Actually, there's no path 1, it's just path dot 0 and 0. And then we'll do this. Right, else we have to do path dot add all path 2. And in fact, we need to do it this way because I need to make it path. I really have to get a formatter for Java. This is not happening, right? So we have to do this to confirm that path 2 need to go to path 1, or we have to do the other way around. Okay, now another time. Oh, actually we can do this. Right, now we do this. Okay. Oh, you're kidding. You're kidding. Oh my god. One of them is out of range. Jesus. Oh, Lord. Alright, so which one is... Well, if path 2 is... And path 2 would not be empty, so this has to be path 1. Right? So we just say if path 1, if path dot is empty, right, is empty, or this. Because if path is empty, we can definitely do this. Alright, this is not right. Wait, you are kidding me. Wait, what? I still do 1, 3, 1, 2. Huh? Path 2 equal to path dot get 0. Wait, which one is path? Path 2. Right? Shall be else path dot add all. Yeah, this is really not make it any simpler. Are we here? Hold a second. Let's give a so we have a path, right? And we have a path 2. We didn't go through here. One, two, three. Okay, this is not right. No, path has to go back to its starting point. It's not true because it can stop here, right? If it stop here, then we should exit. Oh. Yeah, because either you end up in the first or you end up in the second, right? So all right, this one I need to change. If you hear someone that doesn't have anything, first time, then you should exit. Mm. shall quit the first time when I get around. How do I do that? The first time. So either hit yourself, or you hit someone. That does not have anything. We do this one on the outside. We just go one round. Okay. We say while graph dot contains key no1 and graph dot get no1 is not empty. We do this. Right. As we get out, then we merge it with path. Right, we'll merge it with path. We say if path is not empty, path is empty, we just don't do anything, right? If path is not empty, so if temp.get temp.size minus 1 is equal to path.get 0 dot 0, then temp.add all path equal to temp, else what if temp is empty? And temp dot is empty. If both are not empty, right? So else, basically, temp, it has to be the other way around if they're not empty. Then we say path.add all temp. So that's that. So this one is, we'll go through here, and then we'll go through exactly the same thing. I think this one can be a function. Euler path. Alright, so this one we need pretty much the same as here. Probably don't need path. Do need node. Alright, node and node. Okay. So temp, this is node. Alright, path, this is now right. Int. So we use Euler's path for this. Okay, we're gonna note one. I just realized I should pass in the path. Oh, I cannot use get, but that's fine. I just need a peek. At first. At last. All right. Again. What the hell? How did it go from 2-1? My goodness. Yeah, I remember it's 1 first, right? So it should be 1, 2. And then 2, 1. What in the world? Ugh. What? as no 1, right? Maybe I get 1, 3 out first. Yep, I think I got 1, 3 out first. So temp is 1, 3. Path kernel is empty. So it should be just path should be 1, 3. And now is 1, 2. How come 2, 1? What in the world? This is ridiculous. I don't understand. Oh, my bad. I put on the wrong place. Used to know the night Oh, here is the issue. I found the error. I might as well change this one as well. Move first. Wow, we're getting closer to 2.5 hours. I haven't done 2.5 hours for a very long time. And just because it's a holiday. Yeah, it has remove first. What are you talking about? Doesn't have remove first. No such element. Wait, hold on. I think this should be add last. What do you mean by it doesn't have remove first? Array deck does not have remove first? What? Huh? What do you know? It says it doesn't have. I have no energy to deal with this. Like why it's an array deck? Why an array deck doesn't have remove first? I don't understand. Oh, the problem is here. Oh. Yeah, I was like, it doesn't make any sense. Alright. Path, don't remove first. Path. Oh, it does not have remove first. No such element. Wait, which one? It's this one then, right? This one? So you're telling me the path is telling me the path is 0. I see. I see. Yep, this is still not right. I don't know. Maybe we can change it to while. Yeah, I think it's still not right. Oh. I don't know. I'll use this again. This is just a regular traversal. The starting point must have outgoing then incoming. This is the outgoing equals set. Okay, back to the old idea. That's not true. Outgoing is more than incoming. This is outgoing. So I'll say 2 times outgoing is larger than 2 times outgoing is larger than the total. That means we have more outgoing than incoming. Let's try again. Well, we'll have to use this method. Okay, what was the method again? Traverse the graph using DFS. Post-order DFS. Starting from our chosen node, we follow each edge, moving to neighbor nodes and adding each visitor node to our path. This way we ensure that every edge is visited exactly once, creating a continuous sequence that meets the required conditions. As we explore each edge, we add nodes to the path in the reverse order because of DFS, which means we will need to reverse the recorded path at the end to obtain the correct order. At this point you might wonder why we need to use post-order DFS. Wait, what is post-order again? So we will be backtracking, which will also work. Will lead to a TLE issue, the time complexity and basic DFS backtracking, yes. Post-order is you don't add it, you just keep go to the end. Key to optimize is to use post-order. The reason for post-order is we need to perform a DFS traversal with every edge exactly once, and since we are guaranteed a Eulerian path, we know that all edge pair will be visited starting from the correct start node. Crucial part is that we need to ensure that all edges starting from a given nodes are visited before we append that node to the path. Huh? What does that mean? We first explore all the neighbors of a node. Ensure that the reversal respects the rule of visiting all edges from the current node before moving on. To visit all the edges in the correct order and not TLE. First, visit all its possible outgoing edges. It is guaranteed that each outgoing edge will eventually lead back to the start. Right, each outgoing will eventually lead back to the starting node. So the correct order can only be established when all the outgoing edges are visited. There's a reverse path. The path we record is a reverse path. I think I'm going to use the stack again. What? Smash error? Graph node reverse path. Graph node. Okay, we don't have this reverse path. Let's call it rev path. Rev Yeah, this is going to be a stack. And ref path. So ref path will go from right to left. Right, we'll go from right to left. And then okay, the last two, pop it, last two, pop it. Huh, maybe ref path can be hey, ref path can be a stack as well. Right, ref path can be a stack as well. I don't even remember how many times this one is. Three hours actually we're looking at. Alright, I think finally this looks about right. Oh my god. Oh my god. Alright, this one's tough. This one's very tough. The post order is definitely something I did not think about. And also the starting point. Oh, that's not even the Hill-Holz's algorithm. I think I should keep this problem because I need to read this. Hier Holze. No idea what how this one is implemented, but I'll be interested. Yeah, this post order thing is really not. I was not able to get it. You have to visit post order, and the only reason that it works is because it's guaranteed that it will go back to the starting point, right? Because usually with this you use backtracking, because you try a path, if it fail, so you go back, and you try another one. If it fail, you go back, you try another one. That's the difference, right? Because yeah, backtracking is you go this. If it's wrong, you have to track back, and then you try this one. Wrong, you go back, and then you try this one. Okay, you're correct. That's kind of the backtracking, and each time you go out, you have to track back. Go out, try. So this path basically got executed twice, so it's very costly. Now post order means I'll visit this, visit this, visit this, right? And then because even if it failed, and usually if fail means you just go around coming back, go around coming. This is when it means it failed. So you just keep going, keep going, keep going, keep going, keep going, and then in the end, it goes back, right? It goes back to the starting point, and basically from the starting point I go out again, right? I go out again, and go back to the starting point, and then go out again. Then I'll hit at the end, or if I don't hit at the end, I'll go to here. So this will be the last one gets out, and then I start, put everything in. Yeah, that's why it works. That's why it works. But it's very smart. It's guaranteed you only visit each edge once. Right? You visit only each edge once. The others, I guess the important part is also this. Must have one more outgoing than incoming. This is another thing I wasn't realizing. Because if you have the same incoming, same outgoing, yeah, it doesn't really matter. But if you're at the end, that means you have more incoming than you have outgoing, because at the end you have something coming in and not coming out. So that's the end point. That is something I did not realize. I mean, I still wouldn't have passed it, because even if I realized that using the previous method, I went to time out. But that's kind of a different issue, right? So this is important. And of course, Eulerian's path is also very important, because it tells you that the starting point can only be odd degrees. So I'll say 3, right? There's 3 in this. First is Aurelian's path. It lets you know which nodes must be the starting and end point. And the second is the starting point must have one more outgoing than ingoing, right? And the third is you need to use a post order to do the traversal. You have to know all these 3 in order to solve this problem. And of course, we also have this Helmholtz's algorithm, which I don't even know what it is. So we're going to have to read it some other time. Man, this is the longest I have done for a very long time. Every day I try to get only half an hour on this, but I mean, for the past 2 days, every day is about an hour. I think yesterday is actually more than an hour and 15 minutes maybe. And today is 2 hours. No, it's 3 hours. We spent 3 hours on this. Mainly is just the traversal. I couldn't get the traversal to work. I was using all sorts of flags, maps, trying to get it to work, but it does not work. It does not. And I need at least, you look at this, it's so simple, right? When you look at this, when you know the trick, it's so simple. It's always like this. So if you know the trick, it's always simple. If you don't know the trick, dude, it's always bad. Yeah, we start from 8:30 as the first attempt. Look at now, right? That's 3 hours. Exactly 3 hours. And that's actually before I start. I think it's even more than that, because I think I started at 7:30. That's 4. How come it's 4 hours? I lost track of time. I have no idea. I missed my training today. I have to train tomorrow. But I think it's worth it. Once in a while, you really have to do something like this. It kind of, just completely recalibrate your understanding. I don't think this is that complex. I think Aurelian's path I will be able to memorize, and this postorder thing. Yeah, I don't know. But anyway, that will be it. Okay, that will be it for today. I'll see you guys tomorrow. Adios.